Assalamualaikum everyone. My name is Ahmed, Kamran, and my group partner is Sher. Today we'll be presenting the milestone 2 of our fast poison image editing project. This milestone is our performance report and analysis. We implemented and benchmarked multiple parallel backends using OpenMP, MPI, and a hybrid approach, all built around Jacobi iteration. I'll be starting us off, and Alicia will be taking over later on. Next slide. Before we dive into the details, let me give you the big picture. Our best performing backend was OpenMP with 4 threads. It achieved up to 1.81 times speed up over sequential C++ at 512 by 512 images with excellent output quality. PSNR, which stands for peak signal to noise ratio, consistently above 55 dB. MPI with 4 ranks performed better at larger image sizes, giving 1.38 times speed up at 2048 by 2048 images, though with somewhat lower image quality due to an algorithmic difference we'll explain later. Our hybrid MPI plus OpenMP backend was actually slower than sequential C++ at every single image we tested. The synchronization overhead on a single machine completely dominated. And importantly, all C++ backends were between 8 and 124 times faster than our Python baselines, which validates why we moved to compile code entirely. Next slide. Here's the environment we worked on. The hardware was an Intel Core i5-8265U, a 4-core 8-thread processor running Ubuntu 24. We had no NVIDIA GPU available, so CUDA was not an option. We compiled with GCC 13.3 at -003 optimization, used OpenMP, MPI 3.1, and OpenMP 4.5. In total, we tested 9 backends, NumPy and Numba as Python best baselines, sequential GCC and our C++ reference point, then OpenMP and MPI each in 2 variants, with and without adaptive convergence. And finally, the new hybrid MPI plus OpenMP backend we built ourselves, also in 2 variants. The adaptive variants are labeled with the EPS difference. Next slide. Looking at raw execution times, Python is extremely slow. NumPy took 543 seconds at 2048 by 2048 images. Numba took around 320 seconds. The GIL and interpreter overhead prevent any SIMD or cache optimization. Moving to sequential GCC drops that to under 40 seconds, of 13.7 times improvement. And the subquadratic growth we see is expected, since our solver only operates on masked pixels rather than the full image flow. OpenMP is fastest at small and medium sizes, hitting just 2.43 seconds, but at higher image sizes, MPI edges slightly ahead. The crossover happens because the working set at the size overflows the L3 cache, removing OpenMPI's shared memory advantage. The hybrid backend is worst across the board, over 61 seconds at 2048 by 2048 images, slower even than sequential GCC. The culprit is basically the 2 MPI gather recalls per Jacobi iteration compared to just 1 call every 100 iterations in standard MPI. Next slide. This table shows speed up measured relative to the sequential GCC baseline. So GCC is 1.0 by definition, and anything below 1.0 means slower than doing it on a single thread. OpenMP peaks at 1.83 times at 512 by 512 images, but this drops to 1.32 times at larger images as memory pressure grows. MPI shows the opposite trend. It scales better with image size, improving from 1.32 times at 512 all the way to 1.38 times at 2048. The hybrid backend sits below 1.0 at every size, 0.84, 0.82, and 0.64 times respectively. There's no ambiguity here. On a single machine with shared memory, the hybrid approach simply does not. Next slide. Parallel efficiency is speed up divided by the number of workers. So it tells us how productively we are using our available compute. The best we achieved was around 46% for OpenMP, meaning less than half the theoretical capacity is actually doing this work. This is a consequence of the Jacobi kernel being fundamentally memory bound. For every pixel it writes, it reads 4 neighbors, creating 4:1 memory access ratio that saturates the shared memory bus. MPI has a lower efficiency at small image sizes due to communication overhead, but improves as the problem scales. Hybrid sits at just 8 to 10% across all sizes. The per iteration synchronization is completely dominating runtime. The key takeaway here is that no backend exceeds 46% efficiency, and the ceiling is dictated by the memory access pattern of the algorithm itself, not our implementation. Next slide. Now for output quality, OpenMP achieves PSNR above 57 dB and SSIM of 0.9998, essentially indistinguishable from the GCC reference. Interestingly, the hybrid backend matches this quality exactly, because it still uses the same underlying computation. MPI, however, scores around 35 to 36 dB, still visually acceptable but measurably lower. The reason is algorithmic. Our MPI backend uses Jacobi, whereas GCC and OpenMP use a red-black Gauss-Seidel scheme that converges roughly twice as fast. After 5,000 iterations, the MPI solution simply hasn't converged as tightly, and that residual error shows up in the PSN. To close this gap, MPI would need around 8,000 to 10,000 iterations, which comes at additional compute cost. Next slide. Finally, let's look at the actual solver code. For OpenMP, we implemented a red-black Jacobi scheme. Pixels are split into two groups, odd and even endings, and updated in alternating phases using pragma, OMP, and parallel scaling. This avoids data races without any locking while keeping the memory access pattern cache friendly. For MPI, each tank independently updates its slice of the solution for a batch of iterations. That's the min interval parameter. Before broadcasting the full solution vector with MPI bcast, the key design decision here was batching that synchronization every 100 iterations rather than every single one. That is what keeps MPI's communication overhead manageable and is the reason it performs reasonably well at large sizes despite the inter-process automation. You can see the typical benchmark invocation commands shown here, one for OpenMP and one for running MPI across 4 RAMs. Now Alicia will explain further.
Assalamu alaikum. Now I will explain why the hybrid implementation is much slower as expected. Now the hybrid implementation is faster than the previous normal interpretation, but it is much slower as compared to the improved MPI and the improved OpenMP implementation. The improvements were done by us. Now the backend used both MPI and OpenMP together because the thinking was more workers means more faster implementation, but on a single laptop it actually runs much slower because we had a single machine with a single RAM, so there was no actual significant work division, but there was a lot of communication. There was approximately 200 times more communication because you were communicating twice every iteration as compared to 100 times as compared to once every 100 iterations previously in the regular MPI backend. So there was a 200 increase in the communication, and so this is the first cause. The second cause is that MPI is expensive on a singular machine. That we only had one machine, which as I told previously, that we only have one RAM. There was no actual work division over here. And the last is the startup cost, because every time we call MPI run, it spawns two separate OS processes, and each one has to load Python and import these modules and initialize MPI. So a small image size is approximately takes 2 seconds. So a startup alone is the significant chunk of the time. So it would work well on a real cluster where each MPI rank would be on a different physical machine with its own dedicated RAM. Then the communication overhead would be sort of justified because we would be genuinely communicating work. Now MPI has lower PSNR, which was the peak signal to noise ratio. Now MPI produces blurry, or we can say less accurate images because compared to OpenMP because both run the same number of iterations. The reason is because because MPI looks at different version of the data, a different version of each pixels when it updates. MPI uses plain Jacobi iterations. Now imagine if 4 people are updating a section of a spreadsheet. Now we can only look yesterday's version of the neighbor cells, not the current version, not the value in the cells that is being written today. Now everyone works from the same old snapshot. This is safe and parallelizable, but slow to converge. Now after 5,000 steps, we're still not fully accurate over here. And OpenMP hybrid and the GCC implementation use a Gauss-Seidel or red-black implementation, which essentially uses the same spreadsheet, but now we can immediately see what our neighbors wrote this morning. So when we update a red pixel, its black neighbors have already been updated in this very iteration, and so essentially we're working with the freshest possible data. Now it converges roughly 1.9 or 2 times faster than the Jacobi iteration. Now after some, let's say, 5000 iterations, MPI has converged less. Its pixel values are slightly off from the true solution, which shows up as the peak signal to noise ratio of 35 decibels instead of 57, and the perpetual quality is still above 0.99. So images look fine to the eye, but at the pixel level, there exist some gaps. To match OpenMP's quality, we need roughly 10,000 iterations, or we replace the plain Jacobi with some other implementation. Now, in that implementation, the ranks must swap these boundary rows every iteration. That gives us Gauss-Seidel convergence, while keeping the distributed structure, because that is still important. Now, after that, there is this strong scaling analysis. Now, strong scaling means as the image gets bigger with the same number of workers, how does the backend hold up? Now, essentially, if we double the side length of an image, we get 4x as many pixels. So the work should take 4 times longer. That's n square growth. That is the dotted purple line on the chart. Now in GCC, it grows slower than ideal because solver only processes masked pixels, not the whole image, and our test mask doesn't grow as fast as the full image area. In OpenMP, it starts nice enough, but it gets worse at 2048 to 2048, because at that size 3 data arrays take over 50 MBs, and that is much more than the 6 MB L3 cache on my i5 device. All 4 threads, they start competing over RAM bandwidth, and there are not a lot of resources that can go around, so that creates a bottleneck. In MPI it actually improves as size grows, because each rank only holds 1/4 of the data, so its working set fits better in cache. At 2048, by 2048, MPI finally overtakes OpenMP, the only size where that happens. In hybrid, it gets worse and worse. Its communication overhead compounds as the image grows, because it still has to sync twice per iteration regardless of the size, which I told before was a 200 time increase in the communication. Now, instead of always running exactly 5000 iterations, we can add a feature that checks if we have achieved our output or not, and stops early. Now every n iterations, the solver computes the L1 residual, which is the error across all pixels. Now if that error drops below a certain threshold, let's say 0.01, it stops immediately instead of running to 5000. Now at APS 0.01, it never triggers. The residual stays above 0.01 for the entire 5000 iterations for all the image sizes. So OpenMP and OpenMP EPS take almost identical time, because it's never going below the threshold, so it's never actually triggering that thing. The early stopping feature exists. We have implemented it, but it is not actually giving us any significant effect. The threshold is too tight, which means that the recommendation on the EPS is too low. It should be approximately 1 or 1.5, around these values. It should be a loose threshold, so that it can save us 40 to 60% of the compute time with barely any loss in quality. Now at last we have the benchmarking. Now on the top left we can see the source image, and on the top right we can see the GCC reference output. And on the bottom left we can see the OpenMP output, and the bottom right we can see the MPI output. Now the most interesting comparison is the GCC versus MPI. Now if we zoom in into the boundary of the mask region in the MPI, there is a, I think it's visible from here, I don't need to zoom, but there is a subtle color branding in the MPI output. So that's the Jacobi convergence gap. It's basically a bit more visible over here. And here we have the raw data table, which was basically our which we discussed in the previous presentation which we gave before this one, that we would have different performance metrics, we would record different metrics. So these are those metrics which we have recorded in detail. Now this table, it records every image size, every metric, and every backend. So the red numbers show that it's slower than sequential. These numbers, the red numbers indicate that it is slower than the sequential one. The PSNR, the peak signal to noise ratio column, shows that the MPI at 30 to 35 dB versus everyone else at 50 to 57 dB. That is the peak signal to noise ratio column. And the Python backends have no speed up column because they are the well, loosely speaking, how bad can it get reference point? They are the error reference point. And the GCC is 13.7 times faster than NumPy. Just from compiling to native code because, before any parallelism, because the C++ native code will always be faster. Now, conclusions and recommendations. The first is to use OpenMP on this machine. It's the fastest, correct, and simple. No MPI overhead, no MPI overhead, or no processor spawning. And use MPI for large images on a cluster. It gets better as the problem size grows, which is the right property for a gigapixel scale work. And the hybrid should be properly tested and implemented on a real cluster, not on a single laptop, because it would not do justice to it. On two separate nodes or more than two separate nodes, it would genuinely show some significant improvement. And now the epsilon, the EPS value should be loosened from 0.01. It should be from 1 to 1.5, so that the early stopping actually triggers and saves us some time. And at the last, we have fixing the MPI convergence, which is we can essentially swap plain Jacobi iterations with Gauss-Seidel scheme, so that the MPI produces the same quality output as OpenMP without needing twice the iteration. So that was our presentation. To sum it up, the best speedup we achieved was 1.8 times OpenMP, which was OpenMP at 512x512, and 8 to 124 times speedup is how much faster C++ is across Python. And the peak signal to noise ratio was 57 decibels, and the maximum parallel efficiency we achieved was approximately 46%. So thank you.